Welcome to Lecture 15 of CS 182. Today, we're going to continue our discussion of learning-based control from last week and cover reinforcement learning. We'll have two reinforcement learning lectures. Today, we'll introduce the basic concepts and some essential reinforcement learning algorithms, and for the Wednesday lecture, we'll go deeper into some of these ideas. So, to briefly recap some of the discussion from Wednesday, the goal of this part of the course is to talk about how we can go from prediction to control. So prediction problems are problems like recognizing objects in images, recognizing the sentiment from text, and so on. Problems that map a given input to a ground truth output in an IID setting. Control problems instead are problems like controlling an autonomous car, for instance, tasks that require sequential decision making. Prediction problems have IID data, independently distributed data, which means that the output you predict for a particular image won't affect which image you see next, or at least that's your assumption when you construct a learning algorithm, although that's often not true in practice. In control, each decision can change future inputs, so you no longer have this IID assumption. For example, if you turn the steering wheel on a car in a particular way, that would influence what the car's camera sees next. In prediction, you also assume that you have ground truth supervision, whereas in control, your supervision may be a high-level goal. And in prediction, the objective is to predict the right label, whereas in control is to accomplish a given task. So last week on Wednesday, we talked about a simplified setting where we did have ground truth supervision in the form of ground truth actions from a human. In today's lecture, we're not going to have that assumption. And remember, of course, that, as I mentioned last week, these are not just issues for control. In many cases, real-world deployment of machine learning systems, even prediction systems, has these same feedback issues. So even though you assume that the data is IID when you train your, let's say, object classifier, if you then deploy it in the real world, the decisions based on those predictions may actually influence what data your model gets. The example I had last week was a traffic prediction system where you have a model that predicts how likely is there to be a traffic jam, and then you give the results of this model to users, maybe by something like Google Maps, and then users make their decision about where to drive based on those predictions, which may make those predictions not actually come true. So these feedback issues can afflict even regular prediction systems when they are deployed in a real-world sequential feedback loop. So in today's discussion, we'll mostly focus on kind of more classical decision-making domains like this autonomous driving setting, but keep in mind that these same ideas can apply much more broadly. So last week, we talked about how we can make decisions with ground truth supervision, which is imitation learning. In today's lecture, we're going to tackle the problem of high-level goals head-on, where we're going to actually define the full reinforcement learning problem setting, where you no longer have ground truth supervision, and talk about some initial algorithms to try to solve that. Okay, so how do we specify what we want? Before, we specified what we wanted using a set of state action tuples provided by a human expert. And then we could imitate that human expert, and the data implicitly encodes what the human wants the machine to do. But what if we don't have that? And as an aside, we're going to stick with states rather than observations for our discussion in today's lecture. There is a technical reason for this, which will become apparent towards the end of the lecture. For now, just don't worry about it. But the technical assumption we're making now is that whatever you're feeding into your network is sufficient to fully infer the state, meaning that it obeys the Markov property. Meaning that if you get the current observation, the current image from the camera, previous images won't help you figure out what to do. This is not actually true in general, but it's a very convenient assumption to make in reinforcement learning. Okay, so if you don't have these ground truth state action tuples provided by a human expert, how do you know which actions are better or worse? Well, one thing we could do is we can define what's called a reward function. A reward function is a scalar function on states and actions, and it basically gives a score to every state or every state and action. Very often reward functions actually depend only on state, but in general they could depend on both states and actions. And intuitively the score tells you how desirable that is. So if you want to drive a car, you might say, well, the state where the car is driving in the correct direction on the road has a high reward, and the state where the car is in a collision has a low reward. But it's important to note that your goal is not simply to greedily take the actions that will give you the highest reward. It's to actually maximize the reward over the duration of a sequential decision-making process. So if you're going to be driving the car for, let's say, 3 hours, you want the total reward over those 3 hours to be maximized. So at any given instant, for example, you might find that the greedy strategy will just steer the car in the desired direction, even if there's something in the way. Because instantaneously, it won't actually be in a collision right away, so it'll get that high reward for going in the right direction. But if later on that decision results in a collision, it'll then get very low reward. So a greedy decision-making system would just always select the thing that gives high reward right now, even if it leads to disaster later on. A good reinforcement learning system should avoid that. It might make decisions that are less rewarding right now for the sake of being more rewarding later. And that's actually the critical component of reinforcement learning, this notion of long horizon reasoning, the notion that you may choose to do something that is not as good now to reap larger rewards later. So we want to maximize the reward over all time, not just greedily. If we want to maximize it greedily, we could just use the methods from last week, right? Because last week we essentially had algorithms that would greedily try to predict the right action. And you can do that if your supervision is very strong, if it directly tells you which action to take. But if your supervision is weaker, then you need to reason about the consequences of your actions on future rewards. Okay, so let's go through some definitions. So the first thing that we have to define in order to fully specify a reinforcement learning problem is something called a Markov decision process. A Markov decision process is very closely related to a Markov chain, which is named after Andrei Markov, who was a mathematician in the late 19th and early 20th century. Now, the Markov decision process was not actually invented by Andrei Markov. It's actually not entirely clear who it was invented by, but it was very clearly popularized by Richard Bellman in the 1950s. And it's a way to extend Markov chains into the setting where you have actions that you can choose and rewards that you want to maximize. So you can specify a Markov decision process with 4 things. It's actually 5 and sometimes 6 things, but let's just say 4 for now. I'll tell you what the other ones are in a second. But the 4 things you absolutely need are states, actions, transition probabilities, and rewards. So S is a set of states. It's a set. And each state in that set could be discrete or it could be continuous. And it's up to you to define your states. Much like you define the inputs into your neural net for supervised classification, you define your states for a Markov decision process. Those states could be low-dimensional, like, for example, the position of your car on the road. They could even be high-dimensional. You could define your states, for example, directly as the images that are observed by the car's camera, with the important caveat that they do need to be Markovian, meaning that the current image must be sufficient to infer everything that happens in the future, and past images should not be necessary to help with that. It doesn't need to be sufficient to infer deterministically. There can still be randomness in the system, but you can't have a situation where there's something that you can figure out from past images that you can't figure out from the current one. Which is technically not true for autonomous driving, but it could be true for other settings, like if you're playing chess. A picture of the chessboard actually tells you everything you need to know about the state of the game. The other set you have is A, which is the action space. And the action space is a set of actions. And again, the actions could be discrete variables or continuous variables. Together, the states and actions define a controlled Markov process, which is basically a Markov chain with actions. So in a regular Markov chain, you would just have states and you would have transition probabilities. In a Markov decision process or controlled Markov process, you have states and actions, and the probability of the next state, P of st plus 1, depends on st and at. And the transition operator, T, is basically what defines these probabilities. So the T in the MDP definition refers to this probability distribution, and it's sometimes referred to as a transition operator or a transition probability or dynamics. Those are all synonyms for the same thing. Basically the probability of the next state given the current state in action, and often it's referred to as a capital T. And then you have R, which is the reward function. The reward function maps state-action tuples to scalar-valued rewards. Okay. So formally, you can write it as a function from SA to R. Okay. So we can define the Markov decision process in this way. Another object that we can define that is also very useful in reinforcement learning, which we won't talk about at length in this course, but it's just important for you to know about in general if you see it later, is the partially observed Markov decision process. And the partially observed Markov decision process introduces observations into the mix. So in the partially observed Markov decision process, you have states and actions like before, but now you also have an observation space, and you also have an emission probability E. So the states and actions work the same way as before. The observation space is also a set, and that's a set of observations. So you might have, for example, states that are positions of cars and observations that are images. And the relationship between those objects is given by this base net. This is what we saw last week. You have a transition operator like before, but now you also have an emission probability, P of OT given ST. And a reward function, which is again defined on states and actions. Now, we're not going to actually talk about partially observed Markov decision processes. We have only 2 lectures on RL, and they're outside the scope of this class. But if you see them later on in the future, just keep in mind that it's just a small extension on regular Markov decision processes that introduces potentially non-Markovian observations. Some of the algorithms we'll discuss can handle partially observed Markov decision processes very easily, whereas some others really require a fully observed, a regular Markov decision process. All right, so what's the goal in reinforcement learning? Well, we can formalize the reinforcement learning problem as follows. We've got our policy, pi theta A given S, just like before. And again, we'll come back to the partially observed case later, very briefly. The policy has parameters, which we're going to call theta, so those are the weights for every layer in the network. The state is given as input into that policy, and the action is produced as output. And then the world produces the next state according to these unknown transition probabilities, and the next state depends only on the current state and the action chosen by the policy. And then that becomes the new state for the policy. Okay, so that's just the sequential decision-making process. And this sequential decision-making process induces a distribution over sequences of states and actions. So you can say that the probability of seeing state 1, then action 1, then state 2, then action 2, etc., 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 all the way to S capital T and A capital T, can be given as a product of 3 kinds of terms. An initial state probability distribution, which is just determined by the world, times the product over all time of pi theta AT given ST times P of ST plus 1 given ST AT. This formula is just obtained from the chain rule of probability and then applying the independence properties in the Markov decision process base net. Right, so there are certain independencies. For example, the previous state is independent of the next one given the current one, and because of those independencies, when you write out the chain rule of probability, it actually simplifies like this. So that gives us a distribution over sequences of states and actions. And we can define our objective for reinforcement learning in terms of this distribution. So for shorthand, I will refer to sequences of states and actions as tau. So if you see me write P of tau, that really means P of S1A1, S2A2, etc. out to STAT. Tau here stands for trajectory. And you can write down the objective of reinforcement learning as an expected value with respect to P theta of tau. So the optimal parameters, theta, are the ones that maximize the expectation under P theta of tau of the sum over all time steps of the reward evaluated at the state and action at that time step. So to unpack this statement a little bit, the initial state distribution and the transition probabilities, which are defined by the MDP, together with the policy, which is defined by the parameters theta, induces a joint distribution over a full sequence of states and actions, S1A1, S2A2, etc., etc., etc. And the objective of reinforcement learning is to maximize the expected value of the total reward under this distribution. Which is just another way of saying, pick the policy parameters that lead to the largest rewards, except that, of course, any given policy parameters will lead to a distribution over states and actions, so you really want the largest rewards in expectation. It's very important to understand what this objective really means, So if this is a little bit unclear to you, consider adding a comment or coming to class to discuss this. You can also try rewatching the previous couple of minutes of the lecture, because it's really important to understand this objective in order for everything that comes next to make sense to you. Okay. Now, one thing you might note is that pi and p together actually define a Markov chain on SMA. This is a little detail. We're not going to talk about this too much, but there's actually kind of a second higher level Markov chain on its states and actions that's defined by the product of the policy and the transition probabilities. This can be used to derive things like infinite horizon objectives for RL, but we won't talk about that right now.